This module introduces rotary steerable systems, or RSS, a technology that revolutionized directional drilling. The module has been broken down into 3 sub-modules. This is the first sub-module. Across the subsequent 3 sessions, we'll examine why RSS was developed, how it improves drilling efficiency, and its applications. Pay attention to the visuals. They highlight how RSS differs from conventional steerable motors in both concept and execution. By the end of this module, you will be able to explain why RSS is needed, list its categories, recognize examples from industry, and describe its benefits. These objectives guide the session, ensuring that you not only learn about the tool, but also its context. The focus begins with identifying drilling challenges, spiraling, poor hole cleaning, and micro doglegs, which limit the use of steerable motors. We'll then define the types of RSS, highlighting push-the-bit and point-the-bit systems, and discuss leading industry examples such as SLB's power drive. Another objective is to recognize operational advantages: smoother holes, reduced spiraling, improved casing runs, and higher ROP. Each of these points links directly to efficiency and cost savings. Rotary steerable systems were developed in response to key drilling challenges faced with conventional directional tools. Traditional slide-rotate techniques require frequent interruptions to orient the tool face, slowing overall progress and creating inconsistent well profiles. This process also limits the amount of on-bottom drilling time. RSS eliminates these inefficiencies by enabling continuous rotation while steering, keeping the bit engaged for more extended periods and increasing the rate of penetration. Hole cleaning is another concern. Spiraling and micro doglegs from motor assemblies create ledges and cutting beds, raising the risk of pack-offs and stuck pipe, while increasing the possibility of lost in hole. By delivering smoother, more consistent boreholes, RSS reduces these risks. Well placement is also improved. RSS allows for precise trajectory control, ensuring optimal logging data acquisition and maximizing reservoir contact. From a business standpoint, these improvements reduce non-productive time, lower total well costs, and improve recovery factors. In short, RSS addresses the inefficiencies, risks and limitations of steerable motors, representing a step change in directional drilling performance. Here we compare RSS and steerable motors in terms of hole quality. The picture shows 2 wellbore profiles, the RSS at the bottom left with smooth gauge, and the motor top with spiraling and overgauge sections. Interpreting this, RSS produces in-gauge holes, while motors often create irregular shapes that complicate casing and logging. This leads to improved profile, reduced spiraling, and fewer cutting beds. Visually, the smoother line demonstrates reduced micro doglegs, keeping the well closer to plan. RSS delivers not only smoother drilling paths, but also better hole conditions for subsequent operations. From an operational standpoint, this means easier casing runs, less reaming, and improved cementing quality. While steerable motors can meet directional objectives, their compromised hole quality often increases costs later in the well. RSS eliminates many of these issues up front. This slide provides a side-by-side comparison of wellbore geometry. On the motor side, which is highlighted in the top 2 pictures, micro doglegs exceeding 14 degrees per 100 feet are visible, resulting in irregular and enlarged sections. Overgauge holes greater than 10 inches are common, leading to challenges in casing and cementing. On the RSS side below, represented by power drive, the well profile shows micro doglegs of less than 2 degrees per 100 feet and nearly gauge holes. The difference in smoothness is striking. The gauge hole is consistent with RSS, while the overgauge for motors shows unpredictable enlargement. For operations, this translates into reduced torque and drag, fewer reaming runs, and more reliable casing deployment when using RSS. Rotary steerable minimizes spiraling and enlargement. Here we compare hole quality of a motor versus a rotary steerable. On the right, the motor path exhibits irregular curvature with alternating slide/rotate sections creating spirals. The log on the left shows an RSS section that was run after the PDM. It exhibits a continuous, smooth curvature throughout the build. The motor trajectory has micro doglegs that increase drag and casing wear, while the RSS curve is clean and predictable. The log on the right shows how slide drilling causes irregularities, while RSS avoids them by steering while rotating. Operationally, this means fewer reaming runs, improved casing placement, and reduced risk of mechanical sticking. The interpretation is that RSS enables long lateral wells with lower drag, better hole cleaning, and improved bit performance. From a cost perspective, the smoother hole means fewer trips. What we see here is RSS performance in drilling complex well paths. Comparing drilling rates 98 meters per day with PDM versus 193 meters per day with RSS reveals a clear difference in performance. The bottom left picture shows a planned well path in blue compared to the actual delivered by RSS, with the final TD at an inclination of 144 degrees. In the plot to the right, you can see a W-shaped profile comparing planned and actual trajectory. RSS delivers smoother, more efficient curves, even at extreme inclinations. RSS can handle complex well designs that traditional BHAs struggle with. Another takeaway is reduced risk. Smoother holes lower the chance of pack-offs, stuck pipe, and tool failures. Complex paths are no longer prohibitive. With RSS, they can be drilled reliably and economically. This slide shows the limitations of the slide-rotate drilling method. At the bottom, you can see the purple line, which represents the slide sections. In yellow are the survey stations taken by the MWD tool while drilling, and the blue line connects the surveys, providing a best fit inclination. In red is a high-frequency survey taken by a gyro after the run, which shows the changes in inclination between the MWD surveys. What we can see is that during drilling, the well trajectory appears to be smooth and drilling is proceeding according to plan. The red line shows the reality. The motor is dropping during the periods of rotating, and therefore the steered sections have to make up for this and follow the planned well trajectory. It is only when we see the continuous surveys that we notice the large micro doglegs being drilled, which increase torque and drag over poles and reduce the RLP. Eventually, it will limit the lateral length that can be achieved in the well. This slide presents a real example of an RSS well profile. The image shows a smooth, continuous trajectory, free of spiraling or jagged transitions. In contrast to slide rotate wells, the RSS profile demonstrates predictable curvature and precise control. Looking at the chart, the benefit is twofold. Smoother boreholes reduce mechanical drag, and accurate trajectory placement maximizes reservoir contact. For operations, this means easier casing runs, improved cementing, and enhanced logging quality as tools pass freely in the wellbore. The visual also highlights how continuous steering avoids alternating sections of slide and rotate, eliminating associated micro doglegs. The trajectory in the picture is cleaner and closer to the planned design, reinforcing RSS's ability to drill exactly where intended. This slide focuses on RSS's impact on the rate of penetration. The image compares drilling speeds, showing clear gains with RSS. Interpreting the visual, RSS maximizes on-bottom time by eliminating the inefficiencies of slide drilling. Because the tool face is controlled while rotating, drilling continues smoothly without interruptions for orientation. This results in higher ROP while maintaining accuracy. Another interpretation is that RSS enables better energy transfer to the bit, reducing stick slip and vibration that typically slow drilling. The picture illustrates consistent progress, emphasizing that efficiency and accuracy can coexist. Operationally, higher ROP translates directly into reduced drilling days, lowering total well cost. The visuals also suggest fewer reaming runs, since smoother boreholes need less correction. The interpretation is straightforward. RSS is not only a steering tool, but a performance enhancer. It increases drilling speed, reduces downtime, and ensures the well is drilled according to plan. This slide demonstrates RSS's ability to extend the drilling envelope. The image shows two platforms. On the left, wells drilled conventionally are confined within a red circle, indicating maximum reach. On the right, with RSS, blue wells extend far beyond the circle, showing greatly expanded coverage. Interpreting the picture, the same surface footprint accesses much more reservoir volume with RSS. This reduces surface infrastructure, environmental footprint, and overall development costs. It also allows operators to drill from existing pads, extending field life without new construction. The visual interpretation emphasizes that RSS doesn't change the surface geography, but expands subsurface potential. Operationally, this capability enables longer laterals, greater step-outs, and multi-reservoir access, improving project economics. For offshore developments or environmentally sensitive areas, this is a transformative approach. Okay, let's review what we have learned in submodule 1 of 3. You should now understand the need for RSS. Throughout the module, we compared steerable motors and RSS using visuals of hole quality, spiraling, and micro doglegs. We studied traditional slide rotate profiles and contrasted them with continuous RSS paths. Pictures of complex wells, extended envelopes, and drilling rate comparisons illustrated how RSS improves efficiency, hole quality, and operational reach. In the next submodule, we will examine rotary steerable systems and industry examples. Please progress to the quiz. Thank you.